Hi guys. So we are here just to explain something that we missed. So okay, in the last video, this we solved for question 5C. Okay, we are just to check there. Summer 2022, question 5C. This is the part B, the second part of this exercise. Okay, because they asked first for the air standard efficiency for Carnot cycle, and we did. Okay, that was 24 and something like that. So but in the end, okay, in the end of the exercise, in the end of this, okay, if you can see in the end, they asked for determining the power produced if the engine makes 3 cycle per second, and we have to take R also as 0.28 as 0.287 kg by kilojoule by kilogram Kelvin. Okay, now to solve this one we have to understand some theoretical part that are really important and interesting for us. See, first we have to understand this. Okay, so we have just got, we understood, okay, we had this point, they gave us this point, okay, this pressure in the end of the isentropic compression, pressure in the end of the isothermal compression. Then they gave us the lowest pressure in the cycle, P3. They gave us also TL, the lowest temperature in the cycle, that was 300 Kelvin. And we found out what was the highest temperature in the cycle by some calculation for this exercise also, and that was 397.03 Kelvin, if I'm not mistaken. Just you can check the other video and just continue with this one. So now here we want to find what is the work done if, okay, what is the work done if this if the cycle is repeated 3 times per second. Okay, 3 times per second. Okay, if engine produce, okay, it's like determine the power produced if engine make 3 cycle per second. Okay, that's the point. So we know that power is work upon time. Okay, so the point here is how to determine this work here. Okay, how to determine the work here. For cyclic process, we know that the work done will be the difference between the heat supplied and heat rejected. Why? Only because of this one. Okay, we have second law of thermodynamic, Planck's statement. It says that no, there is no, till now, it doesn't exist a machine or an engine that can work with 100% efficiency. It means what? So suppose here I have a heat source. So heat source will supply a certain amount of heat, and this certain amount of heat will be supplied to an engine. This engine will work on this certain amount of heat. Okay, this will be our energy source. So this will produce kind of work, and this work will be how can I say this? This engine will take advantage of most of this part, how can I say this engine will take advantage of almost, he will try to take the more energy he can, okay, from the heat source, okay, that he received, and he will transform this energy into a very useful work done, expressed by this guy QR. Okay, but the point is that technically or theoretically, QS, the heat supply, should be equal to heat rejected, but it's not possible because this engine will also grab some amount of heat. Okay, maybe it's made of metal, so metal will conserve a kind of a part of the heat, and also some friction that it will conserve and things like that. So it will not be impossible to all of this amount of energy that is supplied, all this amount of heat that is supplied into this engine be converted directly into useful work or heat rejected to this sink. Okay, this will be not possible. So where this energy will go? This energy will go directly to this difference, and this energy is that we lose in the engine is given as work done. So work done for cycle, should be cyclic integration of this guy. So yeah, work done for cycle, directly we can just write this will be what? This will be result of the friction between the engine, so that these losses is expressed in this work done. So work done is the heat supplied, or heat transfer supplied and heat transfer rejected. So heat supplied minus heat rejected. So but see, here we have to understand that here heat supply is in isothermal process. Okay, so here temperature is constant, so heat supplied here will be directly converted to work done according to isothermal process. Okay, so QS will be the work done. Why QS will be work done only? Because we know by first law of thermodynamics that heat supplied is equal to W plus delta U, but here we do not have delta U, because delta U, that is a change in internal energy, it is a function of temperature only according to Joule's law. So it depends only of the temperature. So if the temperature doesn't change, it means that there is no possibility to get our internal energy. So all the heat supply will be transformed into work done, okay, work done in isothermal process. The same will happen here. So here we know that from 3 to 4 it is work done, okay, under the same temperature. Okay, now let's go here. So work done is QS minus QR. Okay, we know. Now QS minus QR. We know that QS will be directly converted to work done into isothermal energy. So here I can just write P1 V1 ln upon V, ln of V2 upon V1. Okay, V2 upon V1. This is the ratio, okay, expansion ratio between them. So expansion ratio is always positive, okay, it's always greater than 1. So it's always like this one, 2, okay. So if you are comparing, if you are trying to find the expansion ratio, you have to pick up the greater value. For volume, it will be the greater value upon the lowest value. So we are considering this way. This is the positive way. Okay, so V2 upon V1. So as we know by Boyle's law, okay, Boyle's law, P1 is equal to V1, P1 V1 is equal to P2 V2, okay, when temperature is constant. So from here, you can just take this one. As V2 upon V1, it is the compression, the expansion ratio, it is equal to P1 upon P2. So we can just write expansion ratio regarding P or pressure or regarding volume. It's upon you, and it's upon the data that they gave us. Okay, now see for here P1 V1 ln of V2 upon V1, and here what is P1 V1? We know PV equal to MRT. We just substitute MRT. What is TH? What is T? It is TH because we are working upon this one, upon this state from 1 to 2. It is a constant temperature, and this constant temperature is the highest for this cycle. So that's why it's TH. Okay, TH. Then P1 upon P2. The same will happen here. Okay, here we will have P3, P3, V3, ln of P4 and upon P3. Why P4 upon P3? Okay, why directly Veloso? Only because of this one. See, here it is from 1 to 2, okay, but here it is from 3 to 4. So if you see here, they are opposing in the direction. So you will consider this first one, okay, the expansion direction as the positive direction, and if this is opposing the positive direction, it will be negative. So you will take the same pattern. It will be the highest, or it will be the last upon the last, or the final volume upon the initial volume, as you did here. Okay, so it will be negative. Why negative, Veloso? Because it is in opposite direction according to this one. Negative, okay, negative. Then it will be P3, V3, V4 upon V4. V4 upon V3, final upon initial. Now see, this is minus will come here. So just apply formulas of logarithm, just this minus will be here, and you will get V3 upon V4. You will just make the opposite, okay? So this one, it is the compression ratio, V3 upon V4. And what is V3 upon V4? Do the same rule, okay, as you did for here. Between P3 upon P4, it will be what? P3 times, just right here, okay, P3 times V3 is equal to P4 times V4. So if you just play with this guy, you will get this point. So you got this one. Let me just write here behind this one. Okay, just try to get this one. If you got this point, you got here P4 upon P3 is equal to V3 upon V4. See, if you just do this the same, because they are the same, they are constant temperature. Okay, so this is true. So instead of writing V3 upon V4, I will write P4 upon P3. P4 upon P3, it is the compression ratio. And here, the compression ratio is the same. Then just you have to write this one. P3, V3. What is P3, V3? We know, MRT. But here, from 3 to 4, temperature is lower, the lowest temperature. And we know, lowest temperature is this is the L. MRT. Okay. And Ln, what is the compression ratio? P4 upon P3. We got this from here. Okay. Now it's okay. Why I'm expressing with pressure and not volume? Because I have pressure, I do not have volume. And the last thing you have to know is that the compression ratio in Carnot cycle, the compression ratio and also the compression ratio, this one, and the expansion ratio are the same. So it means that I can calculate this one. I can calculate the work done with this one or this one. So we will use this one because we do not know what is P2, okay? But we know P4 and P3. So we will use P4 and P3 for both cases, okay? So how will it be? It will be in this way, okay? It will be in this way. See, now here, what we have. So here, we will just substitute, okay? We will make this one time, okay? Time what? Time 3 cycle, because they are looking, they gave us a condition, 3 cycle per second, okay? This time 3 cycle per second will reduce this time to 0. It's okay. I will just multiply, okay, the work done to this condition that they gave us. Why I'm erasing here T? Sure, because T here will be 1 second, okay? 1 second, just like this. Then you have just to substitute. So what will be your QR, okay? QR, P will be equal to QS. QS, as we know, just copy it here, and see here, for Carnot cycle, mass is 1 kilogram, 1 kg, okay? For Carnot cycle, mass is 1 kg, okay? For Carnot cycle. Anytime they ask you, mass is 1. So if mass is 1, it means that if we are going to substitute here, mass is 1, for mass is 1, it will be what? It will be RTH for QS, RTH ln of P4 upon P3 minus RT low ln of P4 upon P3. Just multiply by 3 in second. 3 cycle per second. Okay, 3 cycle per second. Then here just find what will be your work done. Not your power. Okay. See, here it is work done. Work done is expressed in joule. Okay, so joule per second will be watt. Watt per cycle. Okay, so now just divide this one. This will be 0.287 time they gave us R 0.7 time TH. What is TH? TH is given there. I guess I wrote here. It's okay. This is 397.03 time ln. What is P4? P4 is 4.5. 4.5 divided by 1 minus 0.287 time 300 time ln of the same 4.5 upon 1. Okay, so you can see here 4.5 upon 1. Now it's okay. Now here, when we calculate this all, we do not forget we have to multiply, okay, by 3. Multiply by 3 per second cycle. Okay, do it all and you get this one 125. Okay, 125, you get this one 125 60 65 watt. Okay, watt per cycle. Okay, so this one will be your power. Okay, hope you may enjoy and thank you very much. I explained a lot because we have to understand where is it coming from and not only doing this one. Okay, thank you very much.